Hey everyone, today I'm going to be talking about some of the solutions to NiteCTF 2022. This was a CTF hosted by the Manipal Institute of Technology. It was a 2-day CTF and overall it had some interesting challenges. These are the challenges I'm going to be covering. Web admin control, 3 under cryptography, 1 under reversing, and 3 under pwn. So let's get started. The first one was admin control. This was a web challenge. It had a lot of solves, and so I figured it was probably going to be fairly simple, and thankfully it was. The first thing I tried was the SQL injection. If you see login page with nothing else, SQL injection is usually a good bet, and surprisingly this just worked on the first try and we get the flag, so nice and simple SQL injection. The next 3 challenges were cryptography challenges. The first one was called Basically I Locked Up. In this challenge, we're given the encryption algorithm and the ciphertext, and we have to recover the original plaintext. So, looking at what we have, this is the ciphertext that was given. It's 64 characters, just looks like jumbled mess. And here's the encryption algorithm. We take a look. Let's make this a little bit bigger. So for the encryption algorithm, it takes a file name and a password. It reads the plaintext from a file, and these next 3 lines are very important. The first one tells us that the password is of length 8. The next one tells us that the password is alpha characters, so just letters. And it tells us that this plaintext exists within the original plaintext. So we're going to be looking for hidden text. This is not actually the case. I'll explain this a little bit more in a second. But next we have the actual encryption algorithm. It's these 2 lines. We can see here it's doing a repeating XOR. So in that password, it's going to cycle over, which is length 8. And so we have a repeating XOR with a little extra, and that little extra is that spice function. And basically it's just doing a bit rotation. We can see OXFF, so it operates on byte size, and it's going to shift it left once and to the right by 7. And we'll get a new, it's just a character mapping, and we XOR that with our repeating key. And then I'll write that into a output file. So we have that output file. So thankfully they already gave us the decryption function. So you can see that this reads the encrypted file. It does the reverse of the spice. So instead of shifting to the left, it shifts to the right. And this one shifts to the left instead of the right. And then it XORs it with our repeating key and then removes the spice. So it does look like the opposite of the encryption function. And then it writes it out to decrypted. So again, our goal is to figure out the password that encrypted our ciphertext and then recover the original ciphertext. So thankfully that's not too hard to do. What was frustrating about this challenge was the challenge was updated halfway through. I'm not sure why. Maybe there was a bug originally, and they changed the known plaintext. So this challenge should have only taken half an hour or so, but I spent maybe about 4 hours just because I was looking for this plaintext instead of the updated plaintext. But once you get this plaintext, again, the challenge is not too bad. What we're going to do is we're going to brute force it character by character. So we're going to guess that the password, we're going to guess different passwords. We're going to say, is the first password equal to A? And then we need 8 bytes of filler, 1, 2, 3, 4, 8. And then we're going to guess B, C, etc. And we're going to see which one of these has the letter H in the resulting plaintext when we call it decrypt on it. A bunch of these are going to have it. I think all of them probably have it. So then we're going to take all of those known results and we're going to try A, and we're going to see if this has the first 2 letters of our known plaintext. And if it does, we're going to keep that for the next round. And if not, we just discard it. And so what's going to happen is basically just brute force it character by character. One thing that's a little bit tricky is you need to actually try every offset. So it's possible that basically not only do you need to try this, you also need to try this and this as your possible keys. 1, 2, 3, 4, 5, 6, 7, 8. All 8 combinations, because it's possible that this plaintext is at a weird offset. And yeah, so if we actually run the script and see what it looks like, Python 3 solve.py, what's happening is these are all the characters that produce the first letter of our known plaintext. These are all the passwords that produce both H and I in our plaintext. This is all 3, 4, 5, and you can see as the keys get longer, it has to match more of this, and so you can see it just gets a little bit faster and faster. And at the very end, these are all keys that produce plaintext that have at least this, I think. And if we look, we can see, you know, high text here. One of these actually has it. Oh, and here it is. Here's our original plain text. It says, oh, you are searching for hide text, and here's the flag. So again, not too hard of a challenge, but I wonder if anyone else was stuck on using the wrong, because I spent a good 4 hours looking for this in the plain text, and I just couldn't find anything. It wasn't until someone in Discord mentioned that the challenge got updated that I saw that they switched to this. So a little bit frustrating, but it is what it is. The next challenge was Shoo-in. So for this challenge, we're going to be breaking a random number generator and then doing some very strange RSA. And we're given 4 files. So let's take a look. Oops. So strangely enough, a bunch of these files are called Python files, but they're not Python files. So we're given this firstnames.py, lastnames.py, primes.py. You can see none of these are Python files, they're just text files. And let's take a look at the actual competition before we look at the code. Cool, so proof of work disabled. So we're given 2 names, and we have to pick who the winner is. So we can guess one, and it says, oh, we lost. And if we guess maybe this one, nope. Cool, we got it, and we made it to the next round. And so you can see we're supposed to predict the winners. So this has a random number generating cracking written all over it, and we'll see that is the actual challenge. So this is the challenge file that was given to us with some slight modifications. First, I just put in a temporary flag so I could run this. So it reads the first names. Again, this isn't actually a Python file, it's just a text file. Last names, primes, it reads all those. This is the class that's used to generate random numbers. We can see it's just an LCG. We have initial values. It takes a seed, A, B, and P, which is pretty standard. It's going to do A.out plus B. If you've seen these before, again, pretty standard. And it updates these by 1, which I don't think is standard, but I could be wrong. I'm not too familiar with all the random number generators. I think normally it just does this line. But either way, there's a function for getting primes, which just reads from the prime array. We're going to see later, gen is just an instance of this. You can see it's using the Python yield syntax, which is pretty cool. So it just calls next, and it'll get the next value, and it also iterates the internal state. There's a function for generating keys. These 2 functions happen at the very end. We'll see that in a second. And this is a custom encryption function that's also used at the very end. So there's 2 parts to this challenge. There's first, you need to construct the random number generator and guess all the fighters. And then at the very end, it gives you some weird ciphertext, and you have to decode the ciphertext. So in my mind, it seems like 2 unrelated challenges, but it is what it is. So we can see here, this is where it constructs that random number generator. So it's going to calculate some random values for C, A, and B, and then it constructs the random number generator, and it builds an instance of the generator. So to calculate these values, A, B, and N, we can see they're all generated just randomly. I think N in this case is 1300. I think either first names or I think one of these has a length of 2000, one of these has a length of 1300. So we know that all of these values are less than 1300, so if we needed to brute force it, we definitely could. Thankfully, the authors were pretty nice to us, and on the very first instance of this fight, the first name and last name of our first fighter, so here would be Rylan Jenkins, they're using the offset for A and B, which were inputs into a random number generator. So if we take this, we can figure out what offset this is, and this is offset A, this is offset B. So we have A and B for the random number generator. And for the second name, so Arnav Montes, they're using 2 calls to gen. So using this information, we can actually just brute force the final seed value. Again, this only goes to 1300, so it's pretty quick to brute force. And from there, we're able to construct a random number generator, the random number generator that's lined up or in sync with the one on the server. And so from there, they just do a call to gen to figure out who the winner is. They do a mod 2. And so for 10 rounds of this, we need to just type in who's going to be the winner. If we do that a whole bunch of times, on the 10th round, they give us a secret message. So they're going to generate some keys, and they're going to print out the results of some encryption, which has the keys, which we'll look at that function in a second. It also has the flag. So here's our secret that we're trying to get, and 1 call to the random number generator. So if we look at the solution file, this is my file that I use to get the results. And so if we actually run it, solve.py, looks like the server died. I'm going to copy this out because just so we can use it. So what the script is doing is it's printing out a bunch of stuff, but basically it tells us that the first winner is 0. It constructs a random number generator, then it prints out the primes that's going to be generated, and from here we just need to get the ciphertext. So the first winner is 0, then 1, and you can see it's predicting, my script is predicting who's going to win. So we're currently looking at Ernest K and Keon Brewer. So Ernest K, the winner is 0, and then another 0, 1, 1, and then 0, 0, 0. Oh, jacks. Oh, another 0. Cool. And at the very end, it gives us our ciphertext. Like I said, this challenge was pretty much 2 challenges, so we're done with this part, and now we need to do some like very strange RSA and get back the flag. So let's look at this generate encryption keys and the custom encryption algorithm. So the generate keys, if you go down and we look at the custom encryption function first, we can see it's using these keys as an argument, but it only actually uses the first 2 keys, 2 key values. So we're only going to look at these 2. The first one is going to generate 2 primes, and so these just come from calls to our next gen. So we need to make sure we hold on to that next gen instance so that we can get the next 2 primes. From there, we need n and g, so n is just the 2 primes multiplied, g is just n plus 1. We can ignore the other 2 values because they're not used. So this is going to generate an n and a g and pass it into here as keys. This is also another call to rand, our random number generator. So we know this, and message is the flag, and we have the output of this function. So we need to reverse this and get back the flag. So this is just, it's really just a math problem. I think I tried to put this into Z3 at first, but nothing popped out. And I think I put it naively into Sage and nothing popped out. So at this point, I just took a quick look. Thankfully, it's fairly simple. I'm just going to go through the math real quick. But basically, we're just solving, the trick is Pascal's triangle and expanding a polynomial, which really isn't as hard as it sounds, if it sounds difficult. I'm not too good at math, so I get scared about this stuff, but really, like I said, this one wasn't too bad. So we're just going to rewrite this into a prettier form. So this was that encryption function, and we can simplify it quite a bit. So first thing I'm going to do is key. I'm going to get rid of this. Instead of calling it key 0, this was actually n, and key 0 was n, and key 1 was g. And so that's, g is just n plus 1, actually, and we're just going to call it n plus 1. We don't need g. So n, we know. N plus 1, we know. Message wasn't message. This was actually the flag. And rand was just a value of rand. I'm just going to call it a because it's just a constant. We know the constants. This is n squared. I'm going to get rid of this because we don't really need it. We're just going to n squared. Oops. And this one is n squared. And it's mod n squared. And all of this is equal to the ciphertext that we are given at the very end of the competition. So we need to solve this for flag. And we actually have everything else, which is nice. So we have ciphertext, the output, we have n, so we know what n plus 1 is, we know what n squared is, we have a, it's just some constant, it was the output of the rand, we have n squared, we have n squared. So we need to arrange this in a form that we can actually solve. So the first thing we can do is, this is all constants, so we can easily calculate this just straight in Python. So n squared, so this is a to the nth to n squared. So we can calculate this, and we can actually just take its inverse and move it to the other side. I'm going to call this a constant, and I think I actually do it up here. Yep, I do it right here. So you can see these are the values. It was some rand, some n to the n squared, and you just calculate the inverse of this value. So it's just to the -1. I'm just going to call this b. Like I said, it's very simple. I just print it out. And then I multiply that by the ciphertext, and then we need to mod that by n squared. But I'm going to keep the modding out of there just to simplify it a little bit. We'll just keep it on the right. Cool. So next we need to figure out how to simplify this. And this is where the actual math trick comes in. So we have n plus 1 to the power of flag, and we're trying to figure out flag, and it's mod n squared. So the trick here is something called Pascal's triangle or expanding polynomials. So if you remember, so we have n plus 1. If we're to do n plus 1 squared, the result is n squared plus 2n plus 1. Cool. If you were to do n to the third, this would be n to the third plus 2n squared plus, is 2n squared? Actually, I think it might be 3. 3n squared plus 3n plus 1. And you can keep going on and on and on. But what's interesting is, so this is mod n squared. Mod n squared of 3n squared is 0 because it has an n squared in it. So if you remember, mod is dividing and then you take the remainder. You can evenly divide 3n squared by n squared. And so because of that, there's 0 remainder. The same for n cubed. You can evenly divide n cubed by n squared, and so the remainder is 0. So mod n squared of this and this are both 0. No matter what the leading coefficient is, it's always just going to be 0 because it has that n squared in it. And so the only thing that isn't going to be 0 when you do the n squared are the last two terms, this 3n and this 1. But technically we're going to do this to the power of flag, which is going to be, some huge number. So, but at the very end, and this is, you can also look at a thing called Pascal's triangle, this thing. Is this one prettier? Not really. Here's one that's a little bit better. Basically, you get these Pascal's triangles. Like I said, we're constructing these, but we're going to construct it to a very large number, and we're just looking at the coefficients that are out front. And let's look at this one. The coefficients that we care about are just these two. All of these, when we mod n, are going to disappear. And so if we look at this value is actually just going to be flag times n plus 1. And so that is the result of this whole power thing. It's just flag plus n plus 1 because we can disregard everything else. Cool. So what we're going to say is that this is just flag times n plus 1. So we can move this 1 to the other side. And now we have something we can easily solve. So we could also do, for some reason, Python doesn't like it when you do inverse of n. I'm not quite sure why, but Sage didn't seem to mind. So I just typed this into Sage. So I put some values in. So I did ciphertext minus 1. So I already multiplied by the b squared. And then flag is message times n. If you just pop this into Sage, Sage has no problem with this. You get this value out. And then if you load it into Python, along from bytes, which is just standard crypto util function, you'll get off the flag. So pretty fun challenge. It was nice to do some math. The next one is itsybitsyrsa. This was a very simple challenge. Let's go back up. So we're given an n value, but we can see this n value is, let me actually go back up, sorry. We're given 3 different values. You have n, e, and c. Can you figure out the message? So this is the ciphertext. This is the encryption key. So if we remember in RSA, we're going to have, it goes e to the plain text is equal to c. And so we just need to figure out the reverse of that. But what's strange is, and it's all mod n, but what's strange about this n is it's absolutely huge. It's almost half a megabyte of just an n value, which in my mind, my guess was that it means that the modulus isn't actually used. It's just going to wrap it. When you do this operation, you're never going to wrap around. And so because of that, we can actually just do a simple root. And so if we look at the c value, decently large value, but this way smaller than n. And if we look at the e value, I had no idea what this was about. It will be given as a question, when did India gain independence? User has to guess the first digits. No idea what this is about. Anyways, I feel like the competition had just a lot of very strange messages that I think were meant for something else. But anyways, we see that the encryption key was 19. So we can solve this very simply by just taking the nth root of this value. And so to do that, let's take a look. Cool, it's right here. So I just loaded the ciphertext value, and here was the encryption key. I used a library called gmpy2 to take the root, and I print it out, and we should just get the flag. Oops. Python 3, and cool. This was the result of the root, and if we load it, here it is. RSA can be very adaptable. We're just doing long to bytes again. So, pretty simple challenge. The next challenge was a reversing challenge called undodge. And we're just given this RAR file. We find out it's actually a Windows executable. And so if we load it in our Windows VM over here, this is the actual game. You can see we're trying to collect these fallen objects. There's something up here that kind of looks like it's decrypting something, and here's our score. So what I first did was I loaded this into Cheat Engine, and I tried to manually change the score. Let me close out of this. I'm not good at Windows. The first thing I tried to do is I loaded it in Cheat Engine. I tried to change the score within there. And when I set it to like score 10 and 100, that top panel, some underscores were showing up. So I wasn't really sure what was going on, but it seemed like it was somehow tied to scores. But instead of messing with that anymore, it was frustrating because I had to Alt-Tab out. I don't know how to do non-full screen, but eventually I just loaded it up into a program called dnspy, which you can use for reversing C# and or .NET and Unity apps. So what we want to do is to use it, you go. This was the file we got. It was called undodged. If you go into the _ data file and then managed, in a Unity application, all the interesting stuff is in a file called assembly C#. I think there's sometimes another one. It's like assembly C# something else, but this one didn't have one. So you just load this into dnspy. If you go over here, this is that thing. You expand. Eventually, you're going to see all these things. It's called flag care 0, 1, 2, 3, all the way here. So these are probably that flag characters that was at the very top of the game. And if we look here, there's a static lookup table, and when the score is equal to 10, it's going to set the text to the value at 26, which is just underscore. So for each of the characters, we can just see what this offset is. This is 22, this is 0, this is 24, this is 4, etc. I just went through, I wrote them all down, and we don't need this anymore. I'm going to close my VM. I wrote those all down into a Python file. So these were those values. Then I constructed that static array. It was just all the lowercase letters and this. And from there, you can just do Python solve and what a player. And it tells you that the flag format is this. So you just wrap that and you have the flag. So the next 3 challenges were Pwn challenges. The first one is too small. Here's a program so small you can't do anything. We're given a netcat port, the challenge binary, libc, I think this was 235, and the linker loader. So this challenge was pretty cool. Let's load it. It asks, what is your favorite movie? Give it some garbage. It says, oh, you like this, and a question mark. We do a quick look at checksec. Files equal to chal. We can see it has full railroad, so we're not going to overwrite the GOT. We see no canary, so we are probably going to do a buffer overflow here. NX is enabled, so we're not writing shellcode. We're going to be wrapping. Pi is enabled, and that's what makes this challenge fun, and nothing else. Cool. After that, let's take a look at Ghidra. So it's not stripped, so we can read the main function. So there's a buffer, it's 16 bytes. We're going to disable buffering on our output. We're going to clear the 16 bytes with zeros using a memset. It asks what our favorite movie is. It reads in 256 bytes into in buffer, so definitely buffer overflow, and then it just repeats it back to us. So what makes this interesting is we only get one input, and then the program exits. Since pi is enabled, we can overwrite the return address. So if we do more than 16 bytes, we should get a segfault, which we do. The problem is, since pi is enabled, we don't know where to jump. And because of that, we can't, ideally we would like to jump to libc, call system, do a one gadget, do some libc wrapping. But we don't have the address. We only get one call. Most likely, since it's doing a printf with a %s, that means it's going to read in buffer until it's null terminated. So if we were to put in 16 A's, we would be able to read values off the stack afterwards. But again, even if we can read values of the stack, we can't jump anywhere since we don't know any address. So we can get a leak, but then the program is already exited and we're done. So what's fun though is we can actually kind of put 2 exploits in one payload. We can both leak and jump to a relative offset that we know is good. And to show what this looks like, so I have my solve script right here. Again, pretty standard stuff. We're importing pwn, blah, blah, blah. I use pwn init to link in the libc on the remote server and the loader. That way everything's the same. Set some debugging, start the process. We can ignore that for a second. I don't actually think we need this now. And we receive until it asks us what our favorite movie is, and then I attach GDB. So, like I said, pi is enabled, so what makes this tricky is we don't know where to jump. All of these addresses are randomized, but pi doesn't randomize all 32 bits of or all 64 bits of the address. It always keeps the last 3 nibbles, so the last 12 bits, it zeroes them out. So that means if all of these values are, the last 3 values are known of an address. So what that means is, if we were to, let's type in 4 values, and let's finish this main function. So we are now in main. If we were to look at the stack, what's going to happen is, here's our buffer. the buffer was 16 bytes long, so this is the first 8 bytes of the buffer. Here's the second bytes of the buffer, the second half of the buffer. Then we have our base pointer here, and then this is where the return call is going to happen. So what we could do is if we were to send 24 bytes, so remember we need to get 2 bugs in one. We both need to leak an address and jump somewhere known, even though pi is enabled. And what we can do is, if we were to fill this with instead 24 bytes of garbage, the printf would happen. And if we were to examine, let's do 32. This would be A's, 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 A's. It would print out all of this to here because of the reverse byte order. And so we would leak this address. But again, what I was talking about earlier, even with pi enabled, this offset is known. So this offset is constant here. And if we were to write one extra A, the extra A would actually go here. And so we can jump to things that are relatively close to that address. And so what does this actually look like? If we were to examine the instructions here, let's do minus 10 maybe. Cool, yep, good enough. So we are going to return to this value within libc when return is called. And we can see this is the code that jumps into main. And the main address is loaded here. So it's going to call RAX. So RAX is presumably main. When we're done, we're returning here. It loads the main address from the stack here. So right now, the program is configured to jump to D90, which we can see on the stack D90. But we can overwrite this last byte. And instead, we could set it to 89. So what will happen is when this function returns, it'll jump here. It'll load the value of main off the stack and just call into main again. So in one payload, we can both leak an address to libc. So we're going to leak this full address. We're not going to know the last one because we're overwriting the byte, but we actually do know it because it's always constant. The last 3 nibbles are always going to be D90. From this, we're going to leak a libc value, and we're also going to jump back and call into main again. Once we have the libc leak, we can then do our standard wrapping. In this case, I tried to do one gadget, but for some reason one gadget wasn't working, so instead I build out ROP. I look for, there was some alignment issue, so you just add an extra ret in there. It just needs to be 16 byte aligned, but then you can search for bin shell, you can call system on it, build out the chain, and they're active. So we can see if this works. Let's find no more G2B, no more this. Exit, let's see if it solves. Loads, we found a, let's go back. So we send our payload. Like I said, we're going to send 24 A's. Then we send that 89 because we want to overwrite that address with 89, which will then call the main function again. Then it received this. It says, oh, you like, and then here's our address. So here's that 89. So we have 7F3E29. So this is the libc address. Cool. Then it says, what's your favorite movie? So we were successfully able to jump back into main, even though pi is enabled. We just overwrote that last byte. Then we're doing the ROT tool, so it's looking for gadgets. We send our second exploit, again, a bunch of A's, and then this is our ROT payload. So this is going to load the address of bin shell and then call system. And then after that, yeah, we should be all set. It should have spawned a shell, and we can see we have shell. So pretty cool challenge. So like I said, in a single payload, we were able to leak an address and jump to a relative offset. Fun challenge. The next challenge was elementary-tcache. This was just a heap exploitation. So we got thread cache. It's been years since I played with the heap. Looks like I still have my mojo. Is this too easy, or is it? So we have the binary, libc. This is 235, and the linker loader, and a NiteCTF port. So loading up this challenge, let's close everything. Don't save, don't save. This was elementary. Let's load Ghidra. Load our editor. And let's take a look. All right, so this is a pretty standard heap challenge. They give us a bunch of options to allocate, edit, free, and view. So we can allocate a chunk. We'll put it in slot 0. We'll give it a byte or a size of 100 bytes. Cool. And then we can edit this chunk, slot 0, enter the contents, A, and then we can view the contents that we just typed in. So we can see A, and then we can also free that. So very standard. What's interesting is there is actually let's take a look at Ghidra. But basically there is a buffer overflow. So we can overflow from one heap chunk to the next. And this is where our vulnerability happens. What makes this fun is they're using libc 235. So it has a lot of the modern protections. So it's not as simple as just, you overwrite and win. We do have to make 2 little changes, but they're really not too bad. So this is the code. You can go through. I mean, it's pretty much what you expect. So it's printing out the menu. It's going to read a bunch of stuff. So this is reading a %d. So we can change this to a C terminated string so it looks a little bit cleaner. It's going to read an int, the slot. Like I said, it does exactly what you would expect. The only thing that's interesting is when it does its scanf right here, we can see it's just doing %s. We can change this one. So this is when you want to enter content. So you're editing a particular bin. You can see you can pretty much just type in as much as you want, and we'll get that overflow. Cool. The other thing to note is if you search strings or you just see there's a win function here, you can see winner, winner, chicken dinner. So they gave us a ret to win function. Let's take a look at checksec. Checksec file. Is it chow? Yep. Partial railrow. So that pretty much tells us what our target's going to be. But keep going through. There is a canary, so we're not going to be doing a stack buffer overflow. We're going to be doing a heap overflow. NX is enabled, so we're not injecting shellcode. No pi. This is very generous of the challenge offers. So it doesn't mean we don't need to leak the main elf address. That we'll know. It's going to be at a constant offset, and no run path, symbols, nothing else interesting. So because we're doing a heap exploit, we're doing a heap overflow. If we were on an older version of libc, we'd probably be looking at the malloc and free hooks, but we're on 2.35, so it doesn't have those anymore. So instead we're going to be overriding the railroad, the global offset table. Cool. The actual exploit, I'm not amazing at heap exploits, so I always refer to how to heap. And basically you just go through this repo and you look for one that'll work. They show this, like I said, this repo is pretty amazing. It shows you all the heap exploits and what they're working on. You can go through, yeah, to make this simpler, we know we're on 235. You can go through here. I think one thing that's frustrating about this is you don't really know where to start. I probably spent maybe an hour or two just kind of looking through the different exploit techniques to see one that would work. I have done tcache poisoning before, and on previous versions of libc, so I kind of know how this one works. And the challenge said elementary-tcache, so I assume it's a tcache poisoning attack, and this is what I ended up doing. But maybe there's probably a simpler way. I'm not too sure. But for this one, if you're going to try solving the challenge and you've never done a heap exploit, I'd highly recommend just downloading this, loading it into or compiling it and loading it into GDB with the correct version of libc. I think the latest version of Ubuntu has 235, and just get a sense for what's happening. But basically, let's see. This is the solve script, so we'll take a look and see what's going on. I think I put in yeah, cool. Okay. So in the solve script, import pwn. I use pwn init to make sure we're using the same version of libc in the loader as remote. We're going to spawn a process. Here are the functions. So we have allocate, edit, view, and free. We have a win address. We have a random ret gadget, which we might need for stack alignment. We have a target, which I'll talk about in a second. And the value we're going to overwrite, just some constants. So it used to be in old versions of libc. When you do a tcache, actually, let's just load it. I'll talk about what I'm talking about. So, tmux. Okay, so it used to be, let's visualize that this is where we are currently. So we have, I created 2 chunks and then I freed them. And because of the way that this malloc works, they're going to go into the tcache bin. So this is the thread local bin, and it can hold up to 7 entries. It used to be, and each one of these, if we look at these, so here's the 2 bins. So we're visualizing the heap right now. Here's a tcache bin, and here's a tcache bin. We can see that they actually point to each other. So we have one, A, C, C9 AD, we can see that these don't quite make sense. Something doesn't seem right. And we can also see that these are the forward pointers. And so they're a single linked list and they point to each other. What's strange about this one is 1ACD. It's just these bytes. It's not these. It doesn't include this 360. So on previous versions of libc, this would just be an exact address to the forward pointer. On 2.35, instead they XOR it with the base of the heap. And so shift with only the top, ignoring the bottom 3 nibbles. So ignoring these values, it's just these. And it's always going to be XORed. So, and you can actually see this here. So we're going to take, it's going to, when you allocate a new chunk off of this free list, it's going to, again, it's going to do that XOR. So if you want to be malicious, you need to know, you have to have a leak to, you need to know these 4 nibbles right here, these 2 bytes, what the address is, or more if it's a, you just need to know the top 64 minus 12 bits. Anyways, in this case, it's just 2 bytes. So first thing first, that means we need to have a a heap leak to get this heap base address. Thankfully, it's pretty easy. What we can do is this is the first chunk I created. So we created a chunk. You're allowed to instantly view the address of the contents of a chunk. And if it was recently on the bin, it'll still contain the forward pointer, which is nice. So we can allocate a chunk, free it, allocate it, and then view it, and it'll print out the contents right here. And so we automatically get a free heap leak. So that's nice. So now we have a heap leak. And now what we're going to do is the tcache poisoning attack, where we're going to take this, we create 2 more chunks, chunk. What we're going to do is we're going to overwrite the contents right here with a target, and our target in this case is going to be the global offset table. We'll overflow this. We'll set this to the value of the global offset table. So the next time we ask for a chunk, it'll actually be a chunk that is the global offset table. So when we start writing data there, we're overwriting the global offset table, and then we can put our win address in there. And so when we call one of those functions, it'll just jump to the win function, and we'll get shell. So recapping, we leaked the libc address by creating a chunk, freeing the chunk, creating the chunk again of the same size, and then reading its content so we get this value. We're now going to then create a chunk, free a chunk. Then we're going to overwrite our original chunk all the way to here. We're going to just fill A. We're going to send OX91 just so this is consistent and malloc the heap doesn't get angry about anything. And then instead of pointing it to where it's currently pointing, we're going to XOR the libc base with the address we want, which will be the GOT, and then we're going to request another chunk, and the chunk that'll be returned will actually be this one, then this one, and then the next chunk returned will be the GOT, and we can start injecting or stuffing our own values into the GOT. And to see how this works, so I put in a break here. I don't know where that goes. Oh, it looks like it went to the win function. So ignoring that, let's actually go here and let's take a look at what the bins look like. So this is after the corruption happens. So we're going to inject a bunch of A's and we're just going to look at the bins. So like I said, we're doing the heap over right now. So we're sending a whole bunch of A's. We send over the OX91, and then this is our injected address. And if we look at the bins, we can see this is a valid heap pointer, and the next bin address in the linked list is actually the set buff global offset table entry. So if we look at this, so right now we're pointing right here. And so eventually when we call malloc, we're going to get a chunk that's actually here in memory, which is pretty cool. So we do that a couple times. Let's put it here and see what we have. Oh, we haven't done the overwrite yet. Actually, we'll put it. Actually, I don't think we can. We can break out the win address though, and see what the GOT looks like. Unable to put a breakpoint at the win address. Strange. I guess that changed. There we go. Okay. So, like I said, we got a chunk to the got, and from there we're able to overwrite some of these values. And so the values we overwrote are, it's actually right here on the bottom. So we were at set vbuff, and I'm now injecting a return address. So instead, when you call set vbuff, it's instead just going to return an address that all it does is return. So basically, I'm just putting garbage in here. So if anyone calls this, they're just gonna trampoline over to this ret call and nothing's gonna happen. Then I'm gonna put the system got value. So this is the initial value. So the way I'd recommend just Googling for how got and PLT works, but instead of an initial trampoline value is put here at first. And when you call this for the first time, the value is loaded. Instead, we're just going to replace it with our initial value. The reason we're writing a bunch of stuff in here is because I think it's doing a scanf and there's a new line appended. And so we need to overwrite this whole thing just so we're respectful with our clobbering. Otherwise, just a bunch of nasty stuff happens. So we're going to actually fill out the entries of all the got. So the first one is we're replacing system. Then we're going to put in our win address at the address of printf. We're going to put in our win address at malloc2, I forget which one gets called first. And then for scanf, we're just putting in ret. And at the very end, right after this, there's going to be a new line as part of our edit function. And so what happens is, I forget, either printf or malloc gets called. As soon as one of them gets called, the win function is called, and then the win function is what spawns shell. So I think I tried putting it here. So I tried allocating a heap at this place, but I think the way it worked, it just wasn't working out well for some reason. I think this address is used as part of the trampoline code, and so it needs to be whatever it was originally. And yeah, I gave up quickly. I think it's also when you create a heap, I think some of these values also get mangled a little bit. So I found it best if I just put it here because I know I'm not using this function call. And then from here, I was able to overwrite these 4 entries. But yeah, once you do that, you win, you get winner, winner, chicken dinner, and you can see the shell spawn. So pretty fun, but yeah, basically just tcache overflow, and we're able to do a tcache poisoning attack. I'm not too familiar with heap exploits, so it's always fun to do one of these. The next challenge was ticket system. We just migrated our ticketing system from C to C++, object-oriented programming for the win. We get a netcat and the same sort of files. So let's take a look. Ticket system. Make Ghidra. Close this. Close this. Cool. So here's the binary. It gives us 3 options. We can add a ticket, edit a ticket, or display a ticket. So if we add a ticket, we get 2 different types. There's normal and priority. We can do A, we get 16 characters. Cool. Looks like we can display tickets. Let's add a ticket of type 2. If we do type 2, we get 128 characters. And we can display, we see both of our tickets, and we can also edit a ticket, ABC. Cool, so not too much exciting stuff. Let's see what Ghidra has to say. We should also run checksec just to see what's going on. Checksec, file, chow. So partial rel row, so we could overwrite that. Canary found, so we're probably not doing a buffer overflow on the stack, but maybe the heap. NX enabled, or we're going to leak it. NX is enabled, so we could be looking for printfs, and maybe with the printf we could leak the canary. NX is enabled, so we're not going to be injecting shellcode, we're going to be wrapping if we do that type of attack. NoPy, also very generous again, so we don't need a address leak to the main executable. If we take a look at the functions, we have this main function. Unfortunately, it is C++, so it means we get all this kind of nasty standard operator stuff, but we can see the main menu here, add new ticket, options, blah, blah, blah. Yeah, it's doing a bunch of stuff. Invalid options, that's it. This stuff is pretty interesting here. So it's using new, and then it's setting a bunch of values to 0, and then it's creating something called a classic ticket. We can see that Ghidra I'm pretty sure it creates these structures for us. Yeah, classic ticket. So it was able to find that with a demangler, and I think we can actually look at the functions. So yeah, we have priority tickets, which has a couple different functions, and base tickets, and a classic ticket. That's cool. Never heard of this. Enter ticket number. Not too much exciting stuff going on. There's this add song option, which is interesting, and we'll take a look in a second. I'm not sure what add song opt is supposed to be, but this is actually the function that you use for editing the ticket contents. But if we look at they said it was a C++ challenge, and so one thing that C++ does is they have these things called virtual tables, and these virtual tables are how you call member functions that belong to instances of the class. And there's one virtual function. If you play, actually, the way I actually found is I just go to strings. I look for interesting things, and that's strange. Search for strings. Search. I don't know why nothing's popping up. That was strange. I don't know why it was different. But anyways, we can see there is a flag. So let's see where this is defined. Flag. Let's look at xrefs. There's something called test function. If we go here, we see that there is a function that is part of the base ticket object that loads the flag for us. So this is technically part of a vtable for some object, but instead I like to just think this is just our ret to win function. Technically it's C++, but we don't even have to worry about it. We just have a ret to win function at this known offset, which is 401750. What makes this challenge easy is that since it's C++, there's these things in memory called vtables, which are basically, when you call a vtable function, it's kind of like calling a GOT member. It's just an address that code will eventually be executed at when you call that function. So if we take a look within, is this tmux python 3 solve.py. Sweet. So let's take a look at the stack. At the heap. So we loaded the challenge, and I just broke about halfway through, and we can see what is on the heap. So we probably saw in Ghidra that they were creating new tickets and putting them on the heap, and they are C++ objects being put on the heap. So that means there should be a vtable entry somewhere there. We can see there's this chunk, which just looks like a generic buffer option, your ticket limit. We can see a heap chunk here, a bunch of twos. So I think this was just an input buffering that they used for copying. If we look here, these are our actual tickets. So I created two tickets, one with 11111, one with 22222. They both have a size of 30 hex. And this first entry right here is actually a link to their vtable. So if we copy this, 403D72, we go there. Here we go. So this vtable, the first address at this thing is add ticket. And they also have an entry for test function. And if we go here, this is the vtable for this object. I created one priority ticket and one normal ticket. We'll see here's their vtable. So they also have a function for classic ticket and base ticket test function. So priority ticket, I guess, implements their own test function. You are not in debugging mode, go away hacker. Interesting. But this base ticket doesn't have that you are not in debugging mode, go away hacker. It just prints out the flag. So, but we can kind of ignore that. Basically what we're just going to do is we're going to do a heap overwrite. We know if we overwrite this value, it's going to execute code. So instead we're just going to place a value there that we want instead, our ret to win function, and we win. So this challenge is pretty simple. Here's the here's the solution script. So we have our three functions that we can do. We can add, edit, and display. What you saw in GDB there is I added two tickets, one with type 1, which is a normal ticket, and a priority 2 ticket, filled them with a bunch of values. Here's our win address. So we're just going to edit the first ticket. We're going to put the win address in a whole bunch of times. Our win address is just here. So it's going to call the function that is at this address. So 44750, which is just the test function base. So it's just like a little trampoline. we're going to corrupt the heap with it, just print it a bunch of times, and then when we call normally when it calls this vtable function, it's to add ticket, but instead, since the pointer is wrong, is instead going to call this function. And I think the add ticket is how you edit the ticket. Enter your ticket data. Yeah, so if you wanted to change the contents of the ticket, that's what that is. So instead, we asked to change the content of that ticket, but that function pointer is no longer pointing to that function, it's pointing to this function, and it'll just print the flag for us. So again, pretty simple challenge, but pretty cool. Anyways, thanks for watching. I definitely had a good time. I think overall it was a little bit frustrating that some of the files were changing during the competition. Definitely wasted quite a few hours just because I wasn't searching for the right key, but the pwn challenges were definitely pretty cool. It was amazing. I think some people solved these challenges in just like 10 minutes. I feel like I'm in the presence of greatness when I see that. So very cool stuff. But anyways, thanks all.